This is Algebra 3, section 7.1. This is going to be part 2 of the notes. Here is the slide where we left off last time, and we're talking about the normal distribution. Here we found SAT scores that represent 68% of the data, 95% of the data, and 99.7% of the data, which comes from the empirical rule. The 68, 95, 99.7 rule. So here's another example. We're going to flip the question around. And suppose that the distribution of scores of 1,000 students for the SAT has a mean of 450 and a standard deviation of 25. We're going to assume that the shape of this distribution is a bell curve, so it's normal. Okay? Now, how many students fell between a score of 425 and 475? Well, with these questions, for the most part, we're going to make things very straightforward, and notice that 425 and 475 is just taking 450 and adding 25 and subtracting 25. So on our bell curve, if I were to represent this graphically, 450 is right in the middle. And if I add 25, that's going to get me to a score of 475. If I subtract 25 from 450, that's going to get me to a score of 425. So this is the area underneath the bell curve we are trying to find out. How many students does that represent? Well, using that 68, 95, 99.7 rule, if we're within one standard deviation, then this area should be 68%. Alright, so now I'm going to use my percent equation. I'm just going to turn that into a decimal. So the number of students should be 68% of the total, which is going to be 0.68 times how many students that took the test. 1,000. So we would expect 680 students to have a score between 425 and 475. How many students scored above 500? So now, when I draw my curve, it's important to note that we are only talking about scores greater than 500. So I'm going to find that 500 mark, which is going to be 2 standard deviations up. So that score right there is 500. And everything above that would be the area to the right. So it's just in the one tail. So that region represents scores greater than 500. Okay, so now, first of all, what percentage is that small area? If it's 2 standard deviations away, then that means that this should be 95% of the data. And that means each tail is half of 5%. So this would be 2.5%. And this would be 2.5%. Okay, so notice that the whole thing adds up to 100. So that little tail above 2 standard deviations is 2.5% of the data set. Now let's take that number So we should have, as a decimal, 0.025 multiplied by 1,000. And that gives us about 25 students. But what if you had a question that was, where does 75% of the data lie? Or how many students scored, say, above a 600 or above 482? So when we don't have nice round numbers like this, we need to talk about a z-score. And so a z-score is a raw score which is converted to standard z-score using a formula. Z equals x minus mu divided by the standard deviation. Where x is the data value, mu is the mean, sigma is the standard deviation. Now, the remark, because the area underneath the normal bell curve is always equal to 1, okay, think about that for a second. The area underneath the bell curve should always be 100%, so that number as a decimal would be 1 when we talk about probabilities, okay? We can find any area using a z-score and a table of standard z values, which shows the area under the curve. We're going to see that shortly. The standard normal table approximates areas to the left of the score. In the table, z-scores run from negative 3.49 to positive 3.49. Let's make up a short example. Suppose that z equals 1. That means that's one standard deviation. Up. Okay, so now here's our bell curve. There's the mean. One standard deviation up would be right there, okay? So if we're z equals 1, the standard table will give you the area under the curve to the left. Okay, so to the left of that score would be approximately 84% of the data. Okay, notice that this is not 68, 95, or 99.7. Let's go down to the table. You see, first, it says standard normal distribution. This is from any statistics textbook. You can find this online somewhere. Not a problem. The area is going to be to the left. Okay? So now, if I look for z equals 1, okay, here's my example. This is z equals 1. So this table has a column, and this column represents 2 the ones and tenth place. Okay, so for example, 3.4. So this is the 1 and tenth. And then this column over here is the hundredth place. So we're always going to have a z-score rounded to the nearest hundredth. If I look for 1.00, 1.0, and then 0, okay? So if I'm looking at z equals positive 1, I get that number right there, which is 0.8413. So in case you're asking or wondering, how did I get 84% for that previous example? It came from this table. And I took 0.8413 and rounded it to 84%. You now know how to read a z-table. So, use a z-table to approximate the area under the curve for a z-score of negative 1.25. So first, I'm going to draw a bell curve. We don't have any data here, it's just z-scores. So by the way, we have to note. So we'll say, note that for the standard bell curve, the mean is 0 and the standard deviation is 1. And that's for z-scores. Okay, so anytime we talk about that word standard, it's the standard bell curve. So we can put 0 here. And that means a z-score of negative 1.25 would be to the left. At this point, please pause the video and see if you can find the area underneath to the left of negative 1.25. See if you can read that from the table. Alright, hopefully you tried it. In my picture here, negative 1.25 is negative 1.25 standard deviations to the left. Now what's the area to the left of the curve? Under here. So my first step is going to be draw a bell curve and label. My second step is going to be read z table to find negative 1.25. That is going to be, I'm on the left-hand side now, negative 1.2, and then 5. So if I read that table there, it looks like 0.1056 is the answer. So that's approximately 10.56%. Area underneath the curve. There you have it. Please comment on this video in order to receive credit, and then have a nice day.